Welcome to Numerical Analysis. Today we are going to explore Euler's method for ordinary differential equations. Imagine you are lost in a thick fog, trying to find your way. You cannot see the path ahead, but you have a magical compass that tells you the exact slope of the ground right where you are standing. How do you use it to reach your destination? That is exactly the intuition we will build today. To understand how this method works, let us continue with our fog analogy. If you check your compass, take one straight step in the direction it points, and then stop to check again, you are performing a step-by-step procedure. If you take very small steps, you will closely follow the true curves of the landscape. However, if you take giant leaps, you might walk straight off a cliff because you ignored how the ground curved beneath you during that long step. This is exactly how Euler's method traces out a hidden mathematical curve. Now that we have a physical intuition, let us look at the mathematics. In calculus, we often encounter an ordinary differential equation, which describes the rate of change of a variable. We write this as y prime equals f of x comma y. Along with this, we are given an initial condition, which is our exact starting point. Euler's method is a numerical technique that finds approximate values for this unknown curve. Instead of finding a perfect continuous formula, it calculates discrete points by assuming the curve is practically a straight line over a very short distance. This brings us to the mathematical engine of our procedure. The formula for Euler's method calculates the next value, y sub n plus 1, by taking the current value, y sub n, and adding the change over a small step. The symbol h represents our step size, which is the small horizontal distance we move forward. We multiply this step size by the slope at our current position, given by the function f. If we decrease the step size h, our straight line approximations stay much closer to the true curve, increasing accuracy but requiring more calculations. Before we move on, let us see this with a concrete visual. Here, the blue curve is the true hidden mathematical function we want to find. We start at the known point x0, y0. The red line represents our calculated tangent slope. By following this straight red line for a horizontal distance of h, we arrive at a new estimated point, x1, y1. Notice the small vertical gap between the red point and the blue curve at the end of the step? That gap represents the error introduced by our straight line approximation. Now that we understand the formula and the visual, let us solve a basic first-order differential equation. We are given y prime equals x plus y, starting at x equals 0, where y is 1. We need to estimate the value of y when x is 0.2, using a step size of 0.1. This means we must take exactly 2 steps. For our first step, we plug our starting values into the slope function, giving us a slope of 1. We then multiply this slope by our step size and add it to our starting height, giving us a new y value of 1.1. Continuing with our second step, we update our position. Our current x is now 0.1 and our current y is 1.1. Because the curve has likely changed direction, we must calculate a new slope by adding these new values together, which gives us 1.2. We substitute these updated values into Euler's formula. Multiplying the step size by the new slope gives a change of 0.12. Adding this to our current height yields our final estimated value. After 2 steps, we find that y at 0.2 is approximately 1.22. Let us apply this to a real-world physics problem. Newton's law of cooling states that temperature changes based on the difference between the object and the room. Our differential equation is T prime equals negative 0.5 times T minus 20. The object starts at 100 degrees and we want the temperature after 2 seconds using a step size of 1. For our first step at time 0, we calculate the initial rate of change, which is negative 40 degrees per second. Multiplying this by our 1-second step and adding it to the initial temperature, we find the object cools to 60 degrees after 1 second. Moving to the second step of our simulation, our current time is 1 second and the temperature is 60 degrees. We must calculate the new rate of cooling because the object is no longer as hot. Substituting 60 into our equation, we find the new slope is -20. This reflects the physical reality that cooler objects lose heat more slowly. We multiply our step size by this new, less steep slope, resulting in a 20-degree drop. Subtracting this from 60 gives us our final answer. After 2 seconds, the estimated temperature of the object is 40 degrees Celsius. Now that we have successfully used this formula, let us understand exactly where it comes from. We will build it from scratch using the formal definition of the first derivative, which you may remember from basic calculus. The derivative represents the exact rate of change at an infinitely small point, written as a limit where the horizontal step h shrinks to 0. However, in numerical analysis, computers cannot divide by 0 or take infinite steps. Therefore, we must drop the limit. By doing so, we accept that our calculation will be an approximation, and we change the equal sign to an approximately equal sign. Continuing with our derivation, our goal is to isolate the future value, y of x plus h. First, we use basic algebra to multiply both sides of the equation by the step size h. This cancels out the fraction. Next, we add the current value, y of x, to both sides. This completely isolates the future value on the left side. Finally, to make this easier to write for a sequence of steps, we replace the function notation with subscripts, where n plus 1 is the next step and n is the current step. This gives us the final famous formula for Euler's method. So, we have proven where the formula comes from. But why is it so important? Euler's method is incredibly valuable because most differential equations in the real world cannot be solved perfectly with algebra. When engineers design airplane wings, they use complex equations to model airflow that are impossible to solve by hand. Video games use these exact principles to calculate the physics of moving objects, updating their positions frame by frame based on speed and direction. While modern computers use more advanced versions, Euler's method remains the foundational building block for all numerical simulations, from weather prediction to space flight. Let us summarize what we have learned today. Euler's method is a powerful numerical tool for approximating the solutions to differential equations. It works by taking small, calculated steps forward along the tangent lines of a hidden curve. We saw that the accuracy of this method depends heavily on the step size. Smaller steps lead to much better approximations, though they require more computational work. Ultimately, this elegant method takes complex, unsolvable calculus problems and transforms them into a repetitive series of basic additions and multiplications. You now have the foundation to understand all numerical simulations.